Okay, good morning and welcome back from our short vacation. I'm glad you're here today, and vacations are never short enough. A couple of updates on information. The lab test that opens up this week opens up today for the Tuesday lab, tomorrow for the Wednesday lab, and Thursday for the Thursday lab. And each one will be open for 10 days. So it's going to be the 17th, 18th, or 19th of September when they end. And again, they're multiple choice. I think it's 50 questions, and you have an hour to answer the questions. So the lecture test will open up as soon as we finish chapter 2. Chapter 2 is one of the longer chapters that we're going to cover, and we will probably finish that up next week. So the lecture test will open up for unit 1 right after the lab test ends, probably. So I don't want to have you having to focus on 2 exams at the same time. Lab this week we will start looking at the skeletal system, and we're either looking at the skull or the axial skeleton today, and we'll continue with that while the lab test 1 is running. So anybody have any questions on anything? Right, the test doesn't close tomorrow. The test opens up today, tomorrow, and Thursday, whatever lab you're in. And you'll have your, because of the, it's the first test, I gave you plenty of time to get ready for it. And I also didn't want to have it closing, keeping it open and closing over the holiday too, because people do things. So anyway, so you have 10 days from today. If you're in the Tuesday lab, you got 10 days from today to take the test. So let's see what else. Right. The test is not closed tomorrow. I changed the due dates. If you looked at the schedule, so I think I changed them for everybody. But I didn't change it. I know I changed it for today's class. I thought I changed it for all of them, but if not, I'll fix it. Nothing closes until 10 days from today, tomorrow, or Thursday. So, any other questions? Okay, in that case, I'm going to go ahead and go back into chemistry. And I know that you just probably couldn't wait to hear how the electrons are making out. So, okay. So we'll jump into it and get through it as fast as quickly as we can with the least amount of pain. Chemical bonding. We just spent last week talking about mixtures. Sand and water, salt and water, glucose, sugar and water, gravel and dirt. All these things are just plain ordinary mixtures. There's no chemical reaction taking place. If you take, even with making a cake, you take the eggs and the oil and the water and the flour and the sugar and the flavoring and whatever else goes into a cake and put it into a bowl together and don't do anything to it, you don't have a cake. You may have physically intermixed those separate ingredients, but you could still filter that batter and extract the oils and extract the eggs. You could probably, if you could take out the water, you could extract all that. You could physically, if you desired to, you could physically separate all the properties of cake batter, because there has not been a chemical change taking place there. It's not been a chemical change. Chemical changes involve the sharing of electrons. And in mixtures, there is no sharing of electrons. If you dump salt into water and make salt water, when the water evaporates, you'll still have your salt. So there's been no chemical change. The salt doesn't evaporate with the water. Same with sugar. If you look at a beaker of sugar water, evaporate, the sugar will be left behind and the water will be gone. No chemical change occurred. Chemical changes involve the use of electrons. It involves the sharing of electrons. Now, atoms, all atoms have electrons. We learned that last week, the week before. All atoms have electrons. We know that the electrons and the protons and the neutrons are considered subatomic particles. Electrons have a negative charge that balance the positive charge of the proton. All atoms except hydrogen have neutrons in the nucleus too. Neutrons don't have a charge. And despite the fact that electrons are very tiny and protons are very big, mass-wise, they're balanced by their charge. Now, atoms want to be stable. They always desire to be stable. They always want their valence shell to be filled up. No matter which shell is their valence shell. Now, the valence shell in an atom is always the last orbit where the electrons hang out. So we know we have electrons in orbit around the nucleus. We know we have electrons. We have 2 electrons in the first orbit, and we have 8 electrons in the second orbit, and we can have 8 or 18 in the third orbit. Whatever the outermost orbit or shell, and I'm going to use shell back and forth here. Whatever the outermost shell around the nucleus is always called the valence shell. Electrons in the valence shell have the greatest amount of potential energy because they don't have to work very hard to keep from being pulled into the nucleus. The electrons in the first shell have to work very hard, so they don't have a lot of potential energy. But atoms want their valence shell to be filled up so they can be stable. So the only, and everybody wants their valence shell to have 8 in there, at least as far as we're concerned in A&P. They want to have their valence shell filled up with 8 electrons, except hydrogen. Hydrogen wants to have 2 electrons in its valence shell. Helium doesn't count because it's already stable. So the driving force behind chemical reactions is always this desire to achieve stability by filling up its valence shell. And atoms are the reactivity of an atom is measured by how rapidly it wants to fill up its valence shell with electrons. Only a handful of atoms have complete valence shells. Helium, neon, radon, argon, krypton, what we call the noble gases on the far right-hand side of the periodic table. They are stable and non-reactive because their valence shells are all filled up. If the valence shell is not full, then the atom is going to be reactive. And atoms will gain electrons, atoms will lose electrons, or atoms will share electrons to achieve this stability. It doesn't do anything. They don't affect the number of protons. They will alter or share the electrons. So now, if you are what we call a chemically inert atom, we consider them to be electrically neutral. They are electrically neutral. They have no charge on them. Helium, 2 protons in the nucleus, 2 electrons in its valence shell. Helium reacts with nothing. There is nothing that helium will react with. Same applies to neon. Its outer shell is the second shell or the second orbital. 10 protons, 10 electrons, 2 in the first orbit, 8 in the second orbit. Neon is stable. Underneath neon, you have the remaining krypton and argon and radon, all stable. all inert gases, all considered what we call the noble gases. They react with nothing. Everything else is reactive. Everything else, all the other atoms are considered chemically reactive. Now, the ones that we're going to pay attention to the most are going to be the carbons, the hydrogens, the oxygens, the sodiums, and the potassiums. Didn't have potassium on here, but we'll get to that. Hydrogen, 1 proton, 1 electron. It would love to have 2 electrons in its valence shell. Carbon has atomic number 6, 6 protons, 2 electrons in its first orbit, 4 in its second. It would love to have 4 more in there to have 8. Oxygen has atomic number of 8, 8 protons, 2 electrons in its first orbit, 6 in its second orbit. It would like to have 2 more in there to be stable. Sodium, atomic number of 11, 2 in the first shell, 8 in the second shell, 1 in the third shell. Sodium would love to have its outer shell stable with 8. Doesn't say how it's going to do it, but sodium would love to have an outer shell with just 8, with only 8 electrons. So it'll achieve stability. So these are all reactive elements. They all want to combine with other atoms to do something about those electrons. Now, so chemical reactions are based on electrons. How do we get a stable number of electrons in the valence shell of an atom? That's the driver behind all types of chemical reactions. Now, we form chemical bonds. So there's 3 types of chemical bonds that we encounter. We have ionic bonds, we have covalent bonds, and we have hydrogen bonds. And ionic bonds show up in salt. They form crystals. Covalent bonds is the most common type of chemical bond, and that's where we get most of our potential energy stored. Hydrogen bonds play a very, very large role in holding water molecules together. So let's take a look at these. Ionic bonds. An atom, a neutral atom that has gained an electron or lost an electron, is no longer an atom. It is now considered an ion. An ion has gained an electron. An ion has lost an electron. It has given up an electron or has grabbed one. The protons and electrons are no longer balanced. The atom has a positive charge or a negative charge. If it gives up an electron, it now has fewer electrons than protons, so it has a positive charge. If it gains an electron, it has more negative charges than positive charges, so it has a negative charge. Ionic compounds that forms through an electrostatic attraction, or maybe like a magnet, where the positive and negative ends of a magnet are pulled together. Ionic compounds are salts: sodium chloride, potassium chloride, magnesium chloride, calcium carbonate. All of these are salts. They form crystals. What will happen in ionic compounds is that one atom gives up an electron and a second atom grabs that electron. So one atom becomes a positively charged ion and the second atom becomes a negatively charged ion, and they are attracted together to form a crystal. Now the crystal has totally different properties than what we started with. I mean, chemical reactions, your products are different properties than what we started with. An ion of, let me go back. An ion of an atom of sodium, when it gives up its electron and grabs onto an ion of chlorine, forms a crystal, which does not look at all like what the sodium atom looked like or the chlorine atom looked like. So we form crystals, and they form this lattice-like structure where we alternate, one ion and the next ion. So that if the green ones are chlorine, the little yellow ones are sodium. They alternate in this pattern. And this is what a crystal looks like. If you look at a crystal under the, look at a crystal, a salt crystal, it will look, well, you won't be able to see the atoms, but you will see the crystalline shape of the structure. The atoms don't look like that. Atoms don't look like crystals, but when their properties change, that's what a salt looks like. In ionic bonds, we are transferring electrons. Sodium gives up its 11th electron, because that 11th electron is out there in the third shell all by itself. It's just spinning around the nucleus, has lots of potential energy, but no love from the nucleus. And so when sodium has a chance, it cuts that electron loose. And now sodium's happy because it has 2 electrons in its first shell and 8 in its second shell. Doesn't matter that it has 11 protons. It has gotten rid of that pesky electron in the third shell. So its valence shell is happy. Its valence shell has 8 electrons in it. So now you have 11 protons and 10 electrons. That sodium atom is now called an ion. It's called a cation. Cations are positively charged. It got rid of an electron. Now, chlorine tends to grab the electron because chlorine has 17 electrons. It has 2 in its first shell, 8 in its second shell. Third shell has 7. If it grabs sodium's electron, it will then have 8 in its valence shell, the 7. So it grabs the third electron, grabs that last electron from sodium, third shell electron, puts it into its third shell. And now chlorine's happy with 2, 8, and 8. That's right, 18, has 18 electrons, 17 protons, 18 electrons. Chlorine has a negative charge on it. It is called an anion. Cations are positive, anions are negative, and they are attracted together electrostatically. They come together like magnets. Electrostatic is just, if you ever use the Swiffer to clean dust off your floor, the Swiffer generates as it rubs across the floor, it generates a negative charge, and it attracts the positively charged dirt, dust, particles on the floor. The only thing wrong with those kind of cleaners is they fill up very rapidly. No matter how clean your floor is, they're going to attract so much microscopic dust and debris that they can't pick up anymore. Anyway, that's just beside the point. Anions and cations, they come together and form crystals. Not a very powerful bond, but we use salt, salt crystals. We use salts in all variations in our bodies. And so, these salt crystals are very important to us. And again, to show you, sort of without the animation, there's the sodium atom right here with that third orbital with the 1 electron. And if sodium kicks that electron out and achieves its stability of having a complement of 8 electrons in its now second shell, valence shell, sodium's happy. It's also positively charged. Chlorine would like to have its valence shell filled up with 8 electrons too. So it grabs that free electron from sodium, gives it 8 in its valence shell. But now they have positive and negative charges, and they are attracted to each other electrostatically. They form the crystals. All salts are made of crystals held together with ionic bonds. And while they're not a very strong bond, they do have an important role to play for us, as we use salts in our bodies all the time, mostly sodium chloride, mostly sodium. Chloride doesn't have a lot to say about the makeup of our body chemistry. Most important type of chemical bond in our bodies are the covalent bonds. The covalent bonds occur not when we grab electrons or give up electrons, but when we share electrons. The covalent bonds involve sharing of electrons in the valence shells of atoms. If we share a pair of electrons, we have a single bond. If we share two sets of electrons, we have a double bond. And if we share 6 electrons, we have a triple bond. So nitrogen, for example, atmospheric nitrogen, N2, is fairly unreactive because it is made up of a triple bond between 2 nitrogen atoms. So nitrogen doesn't combine with a lot of things. The advantage of the covalent bond is that you don't add extra electrons in and alter the charge on the atom or anything like that. Since the electrons are moving at the speed of light, they can be, which is 186,000 miles per second. They can be in orbit around one atom and in orbit around the other atom almost at the same time. For our perspective, it's at the same time. So they're moving so rapidly. If you have 2 atoms that come together and are going to share their electrons, the electrons can be in orbit around the first atom and in orbit around the second atom, satisfying the need to fill up their valence shells at the same time by moving so rapidly. We don't, it's practically impossible, for us. It's challenging to comprehend because it's moving so fast. It's here and it's there and it's here and it's there again and again and again. So that gives the stability that atoms want to have. It fills up their valence shell. Plus, it adds more potential energy to the molecule. Because if you have 2 atoms together, 2 atoms that are sharing electrons are going to have greater potential energy than the atoms did individually. So we're going to fill up our valence shell part of the time, all the time. Meaning it's going to be there, and then it's going to be over here. It's going to be there, it's going to be over here. But it's moving so rapidly, to us, it's a blur. In fact, a picture of it would look like a cloud because the electrons are moving so fast. Now, the covalent bonds, we call it that because the bonding is occurring in the outer shell of the atom. It can be either polar or nonpolar. A polar, we'll get into that in a little bit here. Nonpolar covalent bonds, talk about that first. This is a covalent bond. Up here in the top part of the picture, you see 2 hydrogen atoms. Each hydrogen atom has a proton in the nucleus, so it has a positive charge in the nucleus. The electrons are a negative charge. This is now H2, 2 hydrogen atoms together. The electrons are moving in orbit around each atom. But since they're moving so rapidly, they show up around the first atom, they show up around the second atom, then they're back around the first one. And they're going around both atoms in the valence shells of both atoms, satisfying the need to have the valence shell filled up, in this case with only 2, making this a very stable molecule. This molecule of hydrogen, made up of 2 atoms of elemental hydrogen, is very stable. It's not going to react because it has its electrons. It has 2 electrons there, keeping the atoms happy, if you consider happiness. So that's what, H2, atmospheric hydrogen is not a reactive gas because we have the valence shells filled up. Because remember, chemical reactions are driven by the need to put electrons to fill up the valence shells of an atom. Now, if we take a look at water and hydrogen, hydrogen has 1 electron. Oxygen has 6 electrons in its valence shell. It would like to have another 2 more. A hydrogen atom would like to have 1 more electron. If hydrogen and oxygen come together, hydrogen will share its 1 electron with the oxygen, and oxygen will share 1 of its electrons with the hydrogen. So at any given time, there are 2 electrons in orbit around the hydrogen nucleus, and a 7th electron in orbit around the oxygen nucleus. So the oxygen will work to achieve stability by sharing its electrons with a hydrogen. If we grab another hydrogen, then we've got a water molecule. Now everybody's happy. Because then the oxygen will have its 8 electrons. We haven't added any new electrons to any of the atoms. Hydrogen still has 1 proton and 1 electron. Oxygen still has 8 protons and 8 electrons, but we are sharing additional electrons. We're sharing the electron from each of the hydrogens. And that part of the time gives you 8 electrons in the valence shell of the oxygen. Oxygen is sharing its electrons with the hydrogens, so part of the time the hydrogens have 2 electrons in each of their valence shells. But where this comes into play, and it's really useful to us, excuse me, is in a molecule made up of covalent bonds. Sodium chloride is a molecule that's not made of covalent bonds, so it doesn't have a lot of potential energy. But consider methane. Methane consists of a carbon atom. You see the carbon atom right here in the center. There's a carbon atom. It has 6 electrons, because it has 6 protons on the nucleus. It has 2 in its first orbit, 4 in its second orbit. That means since the second orbit of any atom can hold up to 8, there's room for 4 more electrons. So it's not exactly happy because it doesn't feel stable, even though it's balanced, protons to electrons, even though it's electrically balanced, as we say, electrically neutral. An electrically neutral atom will always be balanced with the same number of protons and the same number of electrons. You might want to make a note about that. Electrically neutral atoms are balanced between protons and electrons. But that carbon atom wants to have 8 electrons in its valence shell, but it still wants to stay balanced. So how's it going to get this 4 more electrons it's going to share with another atom? And the easiest atom to share with is hydrogen. Each one of these hydrogens over here has 1 proton and 1 electron. It has room for 1 more electron in its valence shell, here, 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 and here. And what will happen is that hydrogen will combine with carbon to form methane gas. A molecule of methane gas consists of 4 hydrogen atoms bonded to the carbon atom. They're going to share their electrons in the valence shell. So at any point in time, there are 8 electrons in orbit around the nucleus in the valence shell. In the carbon will be happy because there are 8 electrons in its valence shell. The hydrogens will be happy because the carbon shares its electrons with the hydrogens, and the hydrogens are going to have 2 electrons in its valence shell. So everybody's happy. Are there any extra electrons floating around anywhere? No. You started with 6 electrons in the carbon atom and 4 from the hydrogens. That gives us a grand total of 10 electrons. And we don't have any more than 10 electrons over here. So we didn't add any new electrons. We're just sharing electrons. Not only did we satisfy the carbon atom by sharing these electrons, but this molecule contains a lot more potential energy. Now up here in the corner is the carbon atom right there. 6 protons in the nucleus, 6 neutrons in the nucleus, 2 electrons in its first shell, 4 in its second shell, and now we're going to share 4 more electrons in that second shell. Methane gas has another name. We call it natural gas. It's what we use to power up our hot water heaters, our furnaces, our stoves, our fireplaces, our dryers, all sorts of uses for natural gas. Power vehicles with it, because there is a great deal of potential energy in a molecule of methane. We can burn it. We can release energy by burning natural gas. That's what we do. And we, because in these covalent bonds here, there's a lot of stored potential energy. Those electrons here in this valence shell are the furthest away from the nucleus. So they have greater potential energy than any other electron in the molecule. And that can be used. It can be used as a fuel. If we consider, if you use natural gas at your house, you burn it. You burn that natural gas to release energy. Consider another type of gas that we use as a fuel is called propane. You're probably all familiar with propane. It's the stuff we use. If you have a gas grill, you have a big metal bottle of propane. If you have a big propane tank that, for hot water and for your furnace and for your fireplace and for your stove, and you're using, liquid propane. Liquid propane doesn't have 1 carbon atom; it has 3 carbon atoms and 8 hydrogens, and it has even more potential energy available to use than natural gas does. So propane is, a greater source of energy than methane is. But both of them work because there's a lot of covalent bonding going on here, sharing electrons to achieve stability without altering the number of available protons and electrons, without changing the balance. But by sharing those electrons, we have stability, but we have even greater amounts of potential energy. So we burn propane. We power cars on propane. We heat our houses with propane. We cook on our gas grills with propane, all because of the covalent bonds holding that molecule together. Now, a nonpolar chemical bond, methane, propane. Carbon dioxide, classic example of a nonpolar covalent bond. We say it is electrically balanced. But it lines up in a straight line for whatever reason. Carbon dioxide has an oxygen, a carbon, and another oxygen. Lines up looking like this. The protons and electrons are evenly distributed around here. They don't, there is no preponderance of electrons on one side of the atom or the other side of the atom. They stay balanced. They're evenly distributed. Nonpolar bonds have the electrons evenly distributed. Polar bonds are a little bit different. Polar bonds occur when you have unequal sharing of the electrons. What will happen is that, suppose you have an atom that has let's just say 8 protons, like oxygen. So it has 8 protons in its nucleus, and those 8 protons, 8 positive charges. Now, individually, they're balanced, an electron is balanced by a proton, and a proton is balanced by an electron. But if you put 8 protons together in a mass, they will pull on the individual electrons, and it will cause the orbits of electrons around the nucleus to sort of bend a little bit. So if you have a polar covalent bond, like a water molecule, for example, first of all, water molecules are a little more than a 90-degree angle. So they have sort of an inverted V shape or a V shape. It's actually a 104-degree angle between the oxygens and the hydrogens. So the oxygen molecule, the oxygen atom, has such a powerful draw on the hydrogen atom that the electrons, while they stay in orbit around the hydrogens, tend to be orbiting more frequently around the oxygen side of a water molecule. A polar covalent bond has unequal distribution of the electrons. The orbits are still happy, they're still satisfied, but the orbits are more elliptical than they are circular. So we tend to draw electrons down towards the side of a molecule that has the greatest number of protons. Greatest number of positive charges will tend to pull the electrons down a little bit, and that will give a slight negative charge to that end of the molecule. The other end of the molecule, where you don't have the electrons showing up as frequently, is going to be slightly positive. We say if you can draw the electrons down drastically, they are electronegative, and if not, and if it's less attraction, they are electropositive. And the best example of that is a water molecule. Water molecules are polar. Here's your little hydrogen atom up here. 1 proton, 1 electron, 1 proton, 1 electron. There it is around an oxygen atom right there. This is water. And these electrons here are sort of pulled and twisted towards the nucleus of the oxygen atom, because you have 8 protons here and 1 electron here. And all the electrons, while size doesn't matter here, the individual electrons are individually, I'm redundant. The electrons are being pulled by the large cluster of protons. And so their orbit tends to be more elliptical around here. Yes, they're satisfying everybody's valence shell. Nobody gets left out, but we tend to see the electrons spend a little more time around the oxygen end. And that gives the oxygen end of a water molecule a slight negative charge. It's a long way of saying that. Water molecules are slightly negative on their oxygen end and slightly positive on their hydrogen end, and that makes them polar, because they have a positive and negative end. Now, why is that important to us? Well, polar molecules, like water, form hydrogen bonds. Hydrogen bonds occur when you have the slight attraction to the negative, the positive end of one molecule will have a slight attraction to the negative end of another molecule, just like it. So, we call these hydrogen bonds, you have the positive hydrogen attracted to a negative oxygen, and a negative oxygen attracted to a positive hydrogen, and they come together. It's like magnets again. And these hydrogen bonds occur in water. It's what holds water together. Water is a liquid. When you pour water out onto a surface, it doesn't disappear immediately. It forms a puddle. When you have water in a glass or in a beaker, you see droplets of it along the sides of the beaker, sticking there. Water molecules are going to be held together by their hydrogen bonds. It doesn't sound like a very strong attraction. It's just magnetic, but consider about this. Consider when you try to boil water, or when you boil water. you put water into a container, a beaker, and put it on a hot plate, or put water in a pan and put it on the stove and turn it on high. And you look at it and say, well, why aren't you boiling? Well, it's not boiling yet because it's not hot enough. Water doesn't boil until you start breaking those hydrogen bonds. We have to get to 100 degrees Celsius or 212 degrees Fahrenheit for water to boil. And it takes time to get all the water molecules moving fast enough to break those hydrogen bonds so that boiling will occur. That's how water boils. We're breaking hydrogen bonds. Now, as soon as we turn the heat off and the boiling stops, eventually, all the hydrogen bonds reform. But while the water is boiling, you are busy breaking and reforming and breaking and reforming these bonds. And it takes energy to do that. Just like freezing water. When water goes into an ice maker or into an ice cube tray, and is placed at 0 degrees Celsius or 32 degrees Fahrenheit, it will freeze, but it's not instant. It takes time for the hydrogen bonds, because they're in motion all the time, it takes time for those hydrogen bonds to slow down. It takes time for those hydrogen bonds to slow down enough so they stop moving and water solidifies into ice. And the water, is while ice looks like it's a solid, there's a lot of air trapped inside the ice too. Because remember, ice floats. We'll talk about that further along in the water here. So now, this little animation is not bad at all.
The atoms that make up a water are in a constant temperature.
So the hydrogen bonding is what makes it difficult, makes it not difficult, but what allows water to have a lot of energy put into it to get it to boil. Or it takes a lot of time to slow down that energy, to cool that energy down to get it to freeze. Because remember, every one of those those water molecules is going to combine with 4 other water molecules. And that just spreads out into this massive collection of water molecules. And they create a tremendous surface tension. You've seen water striders run across the surface of a pond or on the river when it's not moving very fast. The surface tension of the water will hold up the water strider. Or you see dust or debris floating on top of the water because the surface tension holds it up. To get water to boil or freeze, to break the surface tension means breaking these hydrogen bonds. So, yeah. Fourth type of bond is not something we encounter a lot of, but we see it maybe every day. We don't think about it as a chemical bond, but it's there. It's called van der Waals attraction. Van der Waals attraction occurs when you have your normal, everyday, non-polar molecule, like glucose, for example. Glucose may be lined up. Glucose forms a ring-shaped structure. So, and it's not it is not polar, but it can be attracted temporarily to another glucose molecule or a fat molecule. Again, not polar. Fat molecules aren't polar, but fat molecules tend to be lined up. Just like glucose molecules are all jammed together with each other, fat molecules are lined up side by side with each other. Occasionally, and that's a relative term, the electrons are in orbit around the atoms of the molecules in fat, for example. There will be a temporary shift in those electrons, like in a nanosecond. Some of them will move all in the same direction, creating a slight positive charge on the surface of that molecule. And that means there's a slight negative charge on another part of that molecule. The molecule next to it, if they go through some sort of transitory temporary shift of electrons, then it will be attracted to the other molecule. So you have one molecule on top of another molecule lined up in, for example, in fat, like in butter. There will be a temporary attraction, and then it'll break and reform, break and reform. Van der Waals attraction is sort of a magnetic attraction between positive and negative portions of large molecules that make that large molecule solid. Butter, animal fat, lard are all examples of van der Waals attraction. Butter is a solid at room temperature. Animal fat is solid at room temperature. Lard, made of animal fat, is solid at room temperature because of van der Waals attraction between the slight positive and negative changes. It's a temporary thing, but it happens so frequently, it appears like it's a constant. Very, very weak arrangement, holding those molecules together. But that explains why fats are solid at room temperature. Animal fats are solid at room temperature thanks to van der Waals attraction. Plant fats, oils, are not solid at room temperature because their molecules are not lined up side by side. Their molecules are sort of wiggly, if you will. So the only way van der Waals attraction works is the molecules are lined up side by side by side by side. So if one changes a positive charge to a negative charge, a molecule next to it will grab onto it and then go and grab on. But plant fats are not lined up in a straight line. They're not lined up in a straight line next to each other. They're sort of squishy looking. So that even if they do have this shift in electrons, they're not going to be attracted to each other. Plant fats, like cooking oils, like olive oil, are liquid at room temperature. No van der Waals attraction going on in plant fats. Just how they're made. Chemical reactions take advantage of this bonding. Chemical reactions will take advantage of this chemical bonding. Will take advantage of the desire of the atoms, if the atoms can have a desire. The desire of the atoms to be stable in their valence shells. So atoms are reactive if they want to force stability in their valence shell. Carbon is very reactive because it wants to fill up its valence shell. Oxygen is very reactive. It wants to fill up its valence shell. Hydrogen atoms are very reactive because they want to fill up their valence shell. Even if it's only 2, they still want to fill it up. So chemical reactions occur to fill up these valence shells. And we form chemical bonds, whether they are ionic bonds or hydrogen bonds or covalent bonds. We will make bonds, we will break bonds, we will rearrange bonds to try and achieve this stability in the valence shell. That's the driver behind chemical reactions, the desire of the atom to get its valence shell filled. Now, I could say that it's desire of the atom to get 8 electrons in its valence shell, but we have some ringers. Hydrogen doesn't need 8 electrons. Sodium doesn't want 8 electrons in its third shell. It wants it in its second shell. So, and so on. But by and large, it is to fill it. We can say to fill the valence shell, and that covers everything, whether it's 2, 8, or 18. Any kind of chemical reaction, and we can use symbols to show a chemical equation, like H2O as a symbol, CO2 as a symbol. Chemical reactions will always contain reactants and products. Reactants are what are the starting points of any kind of chemical reaction. What do you mix together? Or what do you bring together to cause a reaction to occur? If you remember your science fair volcanoes from middle school, you mix baking soda and vinegar together. Baking soda is a base. It is sodium bicarbonate. Vinegar is an acid. It's made up of acetic acid. You mix baking soda and vinegar to get together, and you get the foaming and the bubbling and the fluid and everything. And what you're doing is baking soda and vinegar were the reactants, and your products were what you ended up with. In that case, a release of carbon dioxide and salt and water. Baking soda and vinegar, you get the foaming and the bubbling. Reactants and products. Reactants are what you start with, products are what you end up with. And reactants and products tend to stay balanced, at least outside human systems. In a chemistry lab, reactants and products are balanced. Theoretically, they're balanced in humans also, but we're talking about such small quantities, it's very difficult to quantify. So we consider a chemical reaction. We look at the formula of the reactants, for example, C6H12O6, glucose. Glucose combined with oxygen will yield a release of energy plus carbon dioxide and water. Molecular formula, glucose, C6H12O6 plus 6O2 will give you 6 carbon dioxides and 12 waters and a release of energy. Okay, don't worry about that now. You'll hear about it later on. But that's a formula for a chemical reaction inside the cell. And so we use molecular, we use this all the time now. For our purposes, you're gonna be saying C6H12O6 in your sleep, because that's how we describe glucose, and water and CO2. We'll talk a lot about that, about their role, but it's carbon dioxide, water, and glucose. That's what we're all about when we release energy. There are 3 types of chemical reactions that take place in our bodies. We have what's known as a synthesis reaction. We take small molecules to make large molecules. It is what we call an anabolic or building reaction, anabolic reactions. A plus B yields AB. If we eat glucose, which we do, we take in glucose at the level of our cells will take in all the glucose, a simple sugar. Our cells will take in all the simple sugar it can. Once the cell is completely full, once the cell can no longer take in any more glucose, then any excess glucose will be taken to the liver and form glycogen. Glycogen is the human form of starch. We don't store starch, we store glycogen, which is glycogen's a polysaccharide, and it's lots and lots and lots of glucose molecules linked together. That's an anabolic process. You make a large molecule from small ones. Consider baking a cake again. You take all the ingredients, the oil, the water, the flour, the sugar, the salt, the flavoring, the eggs, whatever, you mix it all together. You create a mixture. You bake that mixture. And that is an anabolic process. The results are a large molecule with lots of stored energy, which has greater energy in it than the individual components did. Anabolic reactions make large molecules out of small ones. If we eat meat, if you eat protein, let's just say you eat a protein. Proteins are made of amino acids, little tiny compounds, little tiny molecules, amino acids. We eat the protein, we break it down into amino acids, and then we reassemble the new protein our bodies need out of those same amino acids. Anabolic reactions take small molecules and make big ones out of it. Their counterpart is a decomposition reaction or catabolic reaction. With a catabolic reaction, we break things down into little things, like you're taking big rocks and make them into little rocks. It is the opposite of the synthesis reaction. It is the opposite of the anabolic reaction. If you eat a piece of that cake, the cake is made of carbohydrates in here, and you eat that cake, it has lots of stored energy in it. You break that cake down from the polysaccharide, the starchy mixture, whatever it is, it's in a cake. You break that down in your body to glucose, and then you release the energy from glucose, and then you give off carbon dioxide and water. You took a large molecule, a large starchy type molecule, and you ended up with carbon dioxide and water and energy. Catabolic reactions give off energy. They take large molecules and break them down into little ones. The third category are called exchange reactions. Exchange reactions have both catabolic and anabolic processes going on at the same time. If you're breaking down protein and making new protein, you're breaking down protein to its amino acids and then taking those amino acids in to make new protein. That's an exchange reaction. You are making bonds and breaking bonds at the same time. We have both synthesis and decomposition, anabolic and catabolic processes taking place. Now, in our bodies, we have something else going on here too. Yes, we are involved, digestion of food is a catabolic process. Building up our muscles is an anabolic process. We also have something going on known as a reduction oxidation reaction, or redox. Or you'll probably hear me call it oxidation reduction, because that's, it sounds easier to say. Redox reactions take place when atoms get reduced. Let me back up and explain that. When you burn something, like you have a fire pit, say you throw a log on the fire pit and the log burns. That's known as oxidation. The log is burning, it's going to give off heat, it's going to give off light, it's going to release carbon dioxide, and it's going to release other gases, it's going to release water, and it's going to be giving off electrons. When you burn something, when you oxidize something, you are releasing electrons. Releasing electrons allows you to release energy, in this case in the form of heat and light. You're breaking down the chemical bonds in the log. Electrons are being released. and energy is getting released. Every time you release energy, you are releasing electrons. Now, the universe doesn't allow that to happen unless those electrons can go somewhere. So the opposite side of oxidation is reduction. Now, reduction in chemist speak means you become more negative. See, what happens is when you burn a log, those electrons are coming off and they have to go somewhere. So something has to grab those electrons. Something has to grab those electrons. And the something that's grabbing the electrons is becoming reduced. And chemists say when something is reduced, it's because it has become more negative. The number of positive charges has decreased. Something has to gain the electrons. So an atom is reduced when it gains electrons and oxidized when it loses electrons. So when you're burning wood, you are releasing electrons and as well as energy. You're oxidizing it. You're burning that wood in the presence of oxygen, and your end result is going to be that fire is going to give off carbon dioxide, it's going to give off water vapor, and it's going to release energy in the form of heat and light. In our bodies, glucose is oxidized and gives off CO2 and water and energy in the form of ATP. Glucose gets oxidized. Oxygen grabs those electrons and gets reduced. So whoever is giving up the electrons is being oxidized. Whoever gains the electrons is being reduced. That's how we'll talk a lot about that when we get into metabolism. So chemical reactions can be catabolic or anabolic. Catabolic reactions are going to be exergonic. They're going to give off energy. You burn a log, that's a catabolic reaction. That's exergonic. You're releasing energy. Endergonic reactions require energy. You're baking that cake. If you mix up all the ingredients and you have a mixture of oil and water and sugar and flour and flavoring and eggs, and you take that mixture and you set it in the oven, don't do anything, you're going to have a mixture just sitting there. If you turn the heat on, that mixture is going to change. It's going to undergo an endergonic reaction. It's going to absorb energy from the heat. You're going to see a chemical change to that mixture and produce a product that is different than what the starting reactants were. And this is an anabolic reaction. Endergonic reactions that require energy are anabolic. We store energy in an anabolic reaction. Endergonic reactions require energy. Exergonic gives them off. Now, a chemist will tell you that all chemical reactions are reversible. And biologists, especially one that teaches A&P, will tell you, yeah, but it's very difficult in the human body for a chemical reaction to be reversible because the reactants and the products in the human body are the concentrations are so small, and the reactants are used up as soon as the products are generally used up as soon as they're made. So while yes, we have anabolic and catabolic reactions all the time, we have displacement reactions all the time, they're not truly reversible in our human body because the concentrations are so small and we use up the products so quickly. Now, a couple of things about chemical reactions that don't really apply to us, but a chemist will argue this. Temperature affects the rate of reactions. The higher the temperature, the faster the rate of reaction. If you are going to make sweet tea, when do you put the sugar in tea? You put it in when the tea is at room temperature, the tea is cold, or do you put it in when the tea is just made and it's still hot? Well, most people put it in when it's hot because the reaction goes, adding the sugar to the tea is going to go faster at a higher temperature. Now, our bodies do a little of this when we have an infection. We have a low-grade fever, 199, 100, maybe 101 low-grade fever here. Our bodies do that to increase the efficiency of our metabolism in attacking and destroying bacteria. So that's a good thing. We can raise our temperature a little bit. But we can't raise our body temperature to increase the speed of chemical reactions normally. Now, we don't like to, we don't work well when we get hot. Concentration of the reactants. Usually, if some is good, more is better. If we increase the amount of reactants, the reaction tends to go faster. We always think that's a good thing. If you are doing your baking soda and vinegar reaction, for example, in your middle school science fair, the more baking soda you start with, the more vinegar you add, the more robust you're going to have your chemical reaction. You're going to have a bigger volcano. It's going to last longer. The judges might even still be there when it's going off. And that's a good thing, usually. But we can't affect the concentration in our bodies because the concentrations are so tiny. We can't increase the concentration. Particle size matters. Size matters. Smaller particles cause the rate to go faster. If you're making that sweet tea, you're not going to throw a 5-pound block of sugar into your tea. You're going to throw a 5-pound bag of sugar in. It's all granulated in there. It's going to go into solution a whole lot quicker. Smaller, I'm conflating smaller and particle. Smaller particles go into solution easier. The rate of reaction occurs faster if the particles are small, but in the human body, particles are already small. So none of that helps us. These are all true statements. Temperature increases the rate of reaction, concentration increases the reaction rate, and the smaller the particle increases the reaction rate, but not in the human body because we can't raise the temperature. We have very small concentrations and we're already very tiny particles. So what we do is we use something called a catalyst. How do we get reactions to go faster? We use something known as a catalyst. A catalyst can make the reaction go faster. Catalysts make the reaction go faster. You're trying to start a fire in your fire pit, and you've got your kindling there, your paper there, and you light the paper, and you're trying to get the kindling to catch, and you decide to cheat a little bit, and you have some fire starters or little pellets or something, and you light those, and they flare up, and they get everything burning real quick, quickly. You would have gotten the fire going with the paper and the wood and the kindling and so on, but it took a while. But if you use these little fire starters, it goes a whole lot faster. Now, enzymes are what we call a biological catalyst that our bodies use to make chemical reactions go faster. Since we're already dealing with very tiny particles to begin with, the concentration is small, the particle size is small, we can't raise the temperature, we can't increase the concentration, and we're already dealing with small particles. So the one thing we can do is flood an area with lots and lots of enzymes. Enzymes are not affected by the reaction or by the reactants. Enzymes are not part of the reaction. They're just like, if you're using a hammer to nail boards together, the hammer doesn't become part of the structure. You're building your deck and you're using your drill using your nail gun. The nail gun doesn't become part of the deck. Enzymes don't become part of the product. They just make the reaction go faster. Enzymes play a major role in our bodies as far as the speed of reactions, and we are very dependent on enzymes. And that leads us into just a few minutes here. Just want to introduce this. Everything we've talked about, so up to now, I want to explain the biochemistry. Allows me to explain the biochemistry of all the reactions taking place in our bodies. The biochemistry, chemistry in biological systems, can either be inorganic or organic. Inorganic chemistry involves water and salts and acids and bases. None of the molecules contain carbon, except carbon dioxide and carbon monoxide. Acids and bases like hydrochloric acid or sodium chloride, sodium carbonate, sodium bicarbonate, sodium hydroxide, hydrochloric acid, phosphoric acid, things like this are acids and bases that we will encounter. Water, obviously salts, sodium chloride, potassium chloride, calcium carbonate. These are all the salts that we encounter: sodium, potassium, calcium, magnesium. None of these inorganic compounds contain carbon. Organic compounds or organic chemistry has often been called carbon chemistry because all the molecules are based off of carbon. The carbohydrates, the fats, the proteins, and the nucleic acids all contain carbon, and they're all covalently bonded. So with carbon chemistry, with organic chemistry, you find that it's lots and lots of large molecules covalently bonded with lots of potential energy. Now, our bodies require both. Our bodies require both organic molecules and inorganic molecules. We are 70% water, so we got to have a lot of water. Water is very important to us. It is the most abundant, as I say, of the inorganic compounds. We don't even think about water because we need it. We get it all the time. But we're about 70% water. Our levels fluctuate. Infant maybe 80%, an elderly person maybe 60%. Well, we're right about 70% right now. Water has high heat capacity. It takes a lot of energy to get water to boil. It takes a lot of water has a high heat of vaporization. It can suck up a lot of heat when it evaporates off your skin to cool us down. It is the universal solvent. Water is used for cushioning, and it is involved in many, many chemical reactions. Most chemical reactions usually involve the formation of water. When we burn something, what do we give off? Carbon dioxide and water and heat and light. So now water molecules they're called a tetrahedron. They're four-sided. They bond. They are a three-sided molecule. Two hydrogens and one oxygen, but they can bind to four other water molecules at the same time. So, what I already said, but water properties: high heat capacity, absorb and release heat very easily. Water keeps us from getting too hot or too cold in our bodies. We use water to help maintain our constant body temperature, right around 98.6. We give off lots of heat we lose heat through evaporation as our cooling mechanism. Water is our solvent that dissolves salts. Our plasma is 0.9% sodium chloride. So, and we use our plasma to transport all sorts of things. The red cells, the white cells, the platelets, hormones and salts and sugars all float in the plasma. And we use water as a cushion around large molecules. Okay, I'm going to stop at salts and pick up with this on Thursday. Lab this afternoon, we're going to start looking at the skeletal system. So let me get out of here. Anyone have any questions on anything? I hope it wasn't too boring. It's going to get a whole lot better very shortly. So we just have to get through this stuff. Okay, then I'm going to get us out of here, and we're going to we'll start. Whoever's in, if you're in the Tuesday lab, I will see you today at 1 o'clock.